Hi guys, it's Teardown time again. Yeah, you think, why the KORAD? This has been shown so many times for so many years. Yeah, for one, it's my trusted power supply that I have for a long time. This is normally standing there. And the idea is not to show you, wow, the features and all these things. We'll go through the schematic diagrams. I will show you the functionality, what the electronics do, and some quirks that I found that I don't like very much. Or let's say so that I don't really understand why they did it. Yeah. For the beginning, this is one of the power supplies I like most. I have it since 2015. It works. I abused it a lot and it still works. Didn't make any problems. The only thing is that it doesn't like impulse loads or some electromagnetic fields, too strong ones, and I will show you why. Okay, let's open it because I already removed the 1 million screws that were attached on the cover. And I hope we have it. Boing. Put it away. Just a fast view of the whole thing inside. My merry-go-round here is sticky. I don't know why. Anyway. I like the transformer where they put it in the middle, center of gravity. We have at the left side the main board with the CPU, A to D, D to A, the everything, the display board behind that, and the keyboard. And on the other side, we have the power board. Let's go a little bit back. Cannot see it very well here. Here we have the power board. Nothing really spectacular till now. But, yeah, on the other side, the bottom, we have the interface board. This is optional. It's not used on every one. It is only if you have USB or serial. But anyway, I have both. So this is how it looks. But as I said, we're going through the schematics and not about the functionality of this thing. So this is the power board. Let's see if we can do it a little bit better. Yeah. On the left side, we have the connectivity to the transformer. This is this thing, this big thing. It's a 36 volt 5 amp transformer. We have two relays that switch between the windings. I think it says when it is rectified 8.5, 27 and 45 volts. It's nothing much to see here. It's just rectification and the series pass element with two parallel power transistors and a driving transistor. That's it. And then it goes to the output. And here we have the over temperature control. That means that somewhere there is, let me see, there is a thermostat. That's all. That when you reach a specific temperature, it cuts out the supply. But okay, this is the power board. This is quite easy. It's nothing really exciting, but this is what I want to show you. This is the this is the front board, the logic board. And we have a main processor. They like to use Nuvoton brand processors. It's an ARM 32-bit ARM. It's quite a powerful processor. It is really, I don't know why they use this processor. Probably because it is so cheap. This thing does everything, almost everything. It controls the relays for the switching of the transformer. It controls the display board. It controls or scans, let's say so better, the rotary encoder and the keyboard. And it reacts or does the action for the overcurrent protection if you set it, and the overvoltage protection. It would just clear the relays. It would just stop the flow through the pass elements. So this is quite, yeah, nothing really spectacular. The only spectacular is that they're using this Nuvoton 32-bit ARM processor, microcontroller. It's a MO54LAN, at least in mine. Additionally, they have an E2 PROM for the settings, to save the settings. I don't know why they don't do it here, but they have an additional I2C, I2 PROM for the settings, that's all. The interesting stuff, okay, on the top here, we have the auxiliary voltages, plus minus 12, plus 5 digital, and 3.3 that is used for the D2A converters. It's a nice detail here that they use. This is either a ferrite bead or a chalk. I don't know. I don't checked it, but it's a nice design here. The whole regulation, yeah. Then we have here, as you can see here, it comes from the power board, goes to this shunt resistor, 100 milliohms, and goes out to the connectors. This is the sensing for the current. And here we have the sensing with this divider here, voltage divider here, for the voltage. These two are nothing else. These two op-amps are nothing else than two differential. They are designed to be differential amplifiers, nothing else. The output of each differential amplifier goes to one of the A to D analog to digital converters. These are 12-bit converters in the ARM, in the microcontroller unit. This is how they read the output voltage and current. But this is only, this here, what you see is only for the reading, nothing else. And yeah, for the overcurrent and over voltage protection, because you set here overcurrent and over voltage a threshold, then if this the threshold, if this voltage exceeds this threshold, it will cut off. That's all. But the whole regulation is this. It's just a standard regulation design with two op-amps and an OR. That means if either one of those diodes is reverse biased, it will cut off the regulation. Whoops, don't see anything anymore. To the power board. So either if the voltage is too high than the set one, it will cut off, or the current is too high than the set one, it will cut off. Till now, nothing really spectacular. Nice, but they do everything analog, and the digital part is only for the non-real things. But overcurrent and over voltage, okay, this thing has to be fast enough to react. But the elephant in the room is this thing here. Guys, this is the A to D converter. these are the two D to A converters for current, set current and set voltage. They are comprised, they use 3 chips, 74 HC595. These are serial to parallel shift registers, and 8-bit one, each one. That's 24 bits. Divided by 2, it's 12 bits. That means they're using 12 bits for the current and 12 bits for the voltage. And the only thing clever in this, what you see here, is that they're using the odd bits for the one setting and the even bits for the other setting, current and voltage. But this contraption here uses 52 resistors. 52 resistors. Why? Why in the name of God you do that? 52 resistors, 3 chips and 2 op-amps, or 1 dual op-amp. Only to make a dual 12-bit digital to analog converter. For what? 52 resistors. Look at that. I will show you how this looks. This is this contraption here. Look at that. How many? All this plus one of these here. Of these op-amps. I don't understand it, why. There are many things that would speak against that. The only thing that I can imagine is they just had this proven design and they had already the code for it. And to be faster, they just use it, and who cares? We have enough space on the PCB. All these things that you see here, this part here, can be done with 2 low-cost 12-bit R2R digital to analog I2C converters. And this would be, for example, the MCP 4725. I will show you the data sheet of that in a jiffy. 12-bit with I2PROM. That means you can save the last one, the last setting, and it is a SOT 23.6. It is a third of the size of SOT 8 or SOIC 8. Yeah. 2 of those would replace all this caboodle here, all this. So, in my opinion, there is no explanation, no excuse why to use this contraption here. The second thing is that because it has so many components, so many resistors, it is susceptible, I think it's the correct word, susceptible to noise. And this is why this thing has problems, the power supply has problems with electromagnetic pulses. All this stuff is quite high ohmic. This is why they use these 2 buffers here. You see? These are only impedance buffers, nothing else. From a higher impedance to a lower impedance. Just to not mess with this R2R network. The last time I used an R2R D2A was in the 80s. I was in the industrial electronics design, R&D, and we had to build a prototype for the voice announcement of an underground train. And at this time, we didn't have any D2As, it was too expensive, etc. And we did our first D2A with using that kind of shift registers or something similar, but 8-bit. It sounded awful, and the prototype was very soon dismissed, and we used ready-made speech output modules. But why? Why do you use that? It is... Anyway, this thing has the R2R network inside, and it's laser trimmed. And it costs under $1 in a larger quantity. So this here, absolutely, this is the only thing I do not like at all, what they did with this power supply. Otherwise, this power supply is really neat, and yeah, except of the shortcomings of the impulse load and electromagnetic pulses that I gave it when I use Tesla coils, etc., or other stuff that high power electronics, it goes crazy. You hear the relays click, click, click. You see the display showing different things. It's going really crazy, yeah? Because it doesn't. This thing changes all the settings all the time. That the noise that comes in. So this is the main board. There's nothing much or more to say. And then we have the interface board. This is the smaller board that I showed you in on the right lower corner. And interesting, they use as a bridge, as a USB bridge, they use again a Nuvoton 32-bit ARM microcontroller. Far too powerful for that to use it for nothing. But okay, why not? The Arduino Uno did that too. Just to use it, just for the USB port, they used a dedicated microcontroller that has more or less the same power that the Atmega 328. So why not? Probably these Nuvoton chips, because it's again a Nuvoton chip, are dirt cheap, probably. And yeah, this is what they bought. But okay, at least it is isolated to the main board completely with 2 optocouplers. It says 2N45, that's bullshit, it's 3N45. But anyway, yeah, there are quite a few interesting misspellings here and typos on the designs, yeah. But at least this can handle, this is the bridge for both the USB and the serial on this side. And this is only just a serial, para TTL to serial interface, nothing else. Yeah. And now the last one is a display. A very, very standard way to use non-specific ICs for a 7-segment display and a few LEDs. Yeah. Again, they are using this 74HC595 parallel to serial to parallel shift registers, and additionally, I think this is a current cathode. Yeah, this is a current cathode 7-segment display, and they are switching the cathodes as they need. And additionally, to display the digits, and additionally the single LEDs that are on the front that show constant current, constant voltage, etc. When they are used, they just, for this small amount of time, everything of this is multiplexed, a small amount of time, they just do not activate they just activate only this transistor here and disable these 4 transistors that would be the cathodes, the common cathodes of both of these 2 7-segment displays. Yeah, and a small 3.3 volt LTO for these 2 chips, and of course for the LEDs. Well, that's more or less the whole interesting stuff that I want to show you here. I like it, even that they use this thing for a dual digital to analog 12-bit converter. it worked, it is working, I abused it, I'm abusing it, and it still works. The only thing is, the two things that I told you, that it doesn't like pulsed loads, really high loads, into the range of the 5 amps that it can give, and electromagnetic pulses. It is quite susceptible because of that, probably, what you see here. Because this thing is a lot of real estate and it's completely exposed. This here, what you see, is the dual D2A converter, including one of these, I don't know which one, or you can check it. U7, that's the upper one, this one. All these parts just for a dual D2A converter that in reality would be the size, you see this one? The size of this one, only with 6 legs. Let me make it a little bit bigger. That's a SOT 23.3. Imagine this one, slightly bigger with 6 legs, 3 and 3 legs on each side. 2 of these would replace all this contraption here. Yeah, as I said, I don't understand it. Nobody designs like that anymore. They probably had it. And most important, they had the code for the microcontroller. So that was a part of hardware and software that they didn't need to care additionally. So they used it. And on the other side, they had a lot of space here, would be completely empty. And yeah, probably workforce doesn't cost anything in China. So this is why they used it here. Yeah, this is more or less my Trusty KORAD power supply that I use as my primary analog power supply. And if you like what you see, if you like my videos, guys, please consider subscribing my channel. That's the shunt. Let me show you again a little bit near. Ring. Please subscribe my channel. Press the like button. Press the ring button, the bell button, ring the bell. All of this would help me to grow the channel, and the ability to show you, make it easier for me to show you a lot of stuff in the future. Teardowns, designs, high power designs, analog designs, anything. I had to do with almost anything, yeah, because everything that is interesting for me, that what is new. So it was just a short video. I go through the schematics here that I wanted to show you. Not how this thing is working, but how are the internals. I hope you liked it. I hope I didn't bore you too much. Okay, then see you next time. Thank you for watching. Cheers. Yeah, I forgot to show you the datasheet of the D2A converter, the 12-bit digital to analog converter. What I would suggest and what I would use. That's the microchip MCP 4725, and that's everything that you need inside. You see here, it has the completely R2R network and the op-amp that they used for the buffering, for the high impedance to low impedance buffer. Everything is inside here. In a small package like that, what I told you, it is a SOT 23.6. Yep, just for info. Cheers, guys. Bye.